Hello everyone, welcome to the first video in this online tutorial introducing you to STELLA from isee Systems for System Dynamics Modeling. My name is Greta Savitsky and I will be bringing you through this tutorial. I am a PhD student at the University of Vermont and I study system dynamics modeling, in particular looking at fire ecology. This is the first installment in a multi-part tutorial on system dynamics modeling and using STELLA software. Today, we're going to be going through what is system dynamics modeling, what is it used for, and in its most basic components, how do we build, analyze, and think about system dynamics models. In future modules, we will be building and analyzing models, but today we'll be going through just some basic definitions and principles having to do with system dynamics modeling. So first of all, what is a system? A system is a collection of interconnected elements or components that work together to achieve a specific purpose or function. Some examples you might be familiar with are ecosystems, which are a collection of biotic and abiotic components, like different plants and animals or different types of soil that all work together to proliferate life. A train system is a collection of trains, rails, and train stations with the purpose of bringing cargo and people from point A to point B. The US government is a collection of individuals and governing bodies with the purpose of creating and upholding laws. And finally, the nervous system is a collection of organs with the purpose of perceiving the outside world and reacting accordingly. When we study systems, it's often helpful to use a systems thinking approach. Systems thinking differs significantly from the prevailing perspective on science or non-systems thinking by being more holistic, focusing heavily on feedbacks and nonlinear behavior. Systems thinking is also often interdisciplinary, meaning that it draws from multiple perspectives. For example, using systems thinking to study climate change would certainly include a climate scientist, but also might include an economist, an ecologist, and a psychologist. Systems thinking also tends to embrace complexity, whereas non-systems thinking tends to be more reductionist, focus on linear cause and effects. It tends to be siloed into single disciplines, meaning that we're not getting that same amount of input from different perspectives. And non-systems thinking often solves problems in isolation rather than looking at large reverberating effects throughout the entire system. If systems thinking sounds interesting to you, I recommend checking out the book Thinking in Systems by Donella Meadows. Here are some of the guiding questions you might use in using systems thinking to think about systems that you're interested in. What is the purpose of the system? How are the parts of the system connected? What are the most important parts of the system and the least important parts? Is the system open or closed? Meaning, can system parts leave the system and come in from outside, or is the system mostly closed off and circumscribed? How is the system organized? Is it uniform or more hierarchical? What is the time scale for the system? And finally, does the system change over that time scale? So if we're using systems thinking in a more scientific context, a lot of the time we will use a formalization of systems thinking called systems theory. This is an academic framework for modeling, simulating, and predicting the behavior of systems used to think about all of the system's parts, how they fit together, how they affect one another, and how they change over time. And systems theory really emphasizes, like I mentioned, the interconnectedness of the system parts and the holistic dynamics of the entire system. To quantify systems theory, we might use dynamical systems theory, which is an area of mathematics used to describe this holistic behavior of complex dynamical systems. And this is usually done using systems of ordinary differential equations to model time-dependent behavior. And here on this slide, we can see the basic setup of a system dynamics model, which uses stocks that measure the accumulation of units in your system, and flows, which measure the change of those units. And we'll get more into that in a different video. Differential equations are equations that relate one or more functions to their own derivatives. And by doing this, we can use differential equations to represent both a variable's current state and its state of change at any given moment in time. And so instead of quantifying a system at a single time point, or even comparing two different time points like non-systems thinking often does, differential equations are able to quantify how the system and its components are changing over time. And this is done because a lot of the time with these complex systems that are constantly changing, it's easier to express how the system is changing rather than looking at the system state at a single point in time. Differential equations are often visualized as vector fields, which we can see to our right here. And we can imagine a vector field as a mountainous landscape. So these arrows show steepness and direction of the metaphorical mountains on the landscape. And by looking at, in this example, just two parameters, we can locate where our system is in time and then see where it is likely to go from there. And so we can use these arrows to show which direction we are likely to move in the future. For example, if we are modeling something like change in a predator population versus a prey population, we would simply find where we are on this map and then follow where the arrows might go. If we land in a place where there are very small arrows, we may not go anywhere. And if we land in a place with very large arrows, we are very likely to move in that direction. Just like any other model, system dynamics models are representations of an object, a system, a process, or an idea. And in particular, system dynamics models are a series of differential equations that represent a complex system. System dynamics models can be used for simulating and predicting systems, and this is done through numerical solution to the ordinary differential equations. And system dynamics modeling can also be used to attribute causality to system behavior through combining model assumptions, iterative model building, and validating your model against the real world, plus performing sensitivity analyses to show how different system components are affecting overall system behavior. That is all we are going to cover in this video for now. In future videos, we'll talk more about some of the patterns that system dynamics models are really great at picking up on, and go into how to build models and how to analyze them. But for now, here are some takeaways. A system is a collection of interconnected parts. Systems thinking is holistic and interdisciplinary. Systems theory and systems dynamics theory are academic frameworks for studying these complex systems. And finally, system dynamics modeling uses differential equations to track system behavior over time. Thanks for watching, and please join me in my next video to learn more about system dynamics modeling. Thanks for watching.